Alright, applications of Amperes Law continued. Amperes Law applications. And so now what we have is another problem that shows up on your worksheet, which is find the magnetic field of a solenoid. So here's a solenoid. Now before we... Alright, so let's start with this. This problem is actually rather easy, or at least easier than the previous one we've done, but I still think it will take some time because there's a bunch of concepts here to go over. But so let's start with just a single loop. Let's say you have a loop and a loop of wire around and comes back like this. So the current flows into the wire and then roams around and comes back out. Now this is going to have a magnetic field. Every current will have a magnetic field, but use the right hand to determine the direction of the magnetic field. So you take the thumb of your right hand and you point it in the direction of the current. It flows like this. Take the thumb of your right hand, point it in the direction of this current, and then curl your fingers, and your fingers will curl like this. This would be the magnetic field around this section of the wire here. If you move a little farther out and you do the same thing, you would then find that the magnetic field does this. And so on, and this is something I already showed you. If you were to go on the other side, here the current flows in this direction. It flows in this direction. This is where the current flows. Take the thumb of your right hand, point in this direction, and then curl your fingers, and you would find that magnetic field here does this. So here you'd find that the magnetic field does point like that around the wire. I'm not sure if this is actually, but anyways, so there's that. Now what we want to figure out is what will happen with these magnetic fields if you were to stack the loops one on top of another one. So let me redraw this, but now I'm going to do two different loops. So let's say you have a loop here. Maybe I can do a better job with this one. And here's a loop. Well, that's better. So the current flows into this wire, goes all the way around, and then it comes back out. All right, so let's draw magnetic field just at these two locations here. So you curl your fingers, you end up with a magnetic field doing this. Move a little farther out and the magnetic field will curl like that. Well, I think the first one came out better than the second one. Anyways, now let's take the second loop and let's put a second loop above it so that we have a second loop directly above this thing. That I have this here and then a loop that roams around, comes back and back this way. So I have a current that flows in here. One loop on top of another loop. And then let's see, let's try to figure out what happens here. So you have the magnetic field at this location and does something very similar. You curl your fingers and you end up with this. This location you curl your fingers and you end up with this. And then you could go all the way around the two loops, but for the sake of clarity, let's just stop here. Let's consider this little section of both of these wires. This magnetic field around this section of the wire is going to combine itself, overlap with magnetic field. That's going to overlap this magnetic field. You're going to get you're going to get kind of a loop like this. Likewise, the magnetic field here is going to overlap with this one, and they will connect, form one single loop. So that if I were to draw a bunch of these, this comes in and then I have a bunch of these wires that go like this, bunch of these loops that do the following. So the current flows in, current flows out. What I would end up with is a magnetic field that somewhere on the inside starts there and then it goes, maybe wiggles a little if you're close enough, comes back and goes back inside, and then on the inside it comes back up. It goes back up, on the outside it goes down, and it does the same thing all over the place everywhere here. So if I were to redraw it a little differently and just sort of do this, let's say that this is the solenoid and this by the way is a solenoid. If you have a single wire and the single wire is wound into a coil like this, then we would refer to this as the solenoid. Let me point this out. Solenoid. note that if you just stack up wires, separate wires on top of each other, that's not a solenoid. You need to have one continuous wire to have a solenoid. But anyway, so now suppose that you have this solenoid and, you know, this thing comes in and then goes around and it loops and it loops and loops and loops and loops and loops around. Bunch of different loops, and then the wire eventually, somewhere on the bottom, eventually wire comes out. The current flows in, goes through this thing, and then the current flows out. You would have a magnetic field that would look like this. On the inside, the magnetic field that points like that, whether it points up or down would be determined by the direction of the current. Is I can try to do that, so this would be actually into the page, so this would be this way. And you would have, and then this loop, this would loop all the way around, and this would loop all the way around, and maybe I'll put one more so that you have that looks like magnetic lines. Okay, and this would be the south pole and this would be the north pole, and this effectively would look like the magnetic field of a magnet. So this is what this picture here is referring to, that the magnetic field lines of a solenoid would look like this. Okay. All right. Let's clear this up because I don't think we need this anymore. You can always, if you need these pictures, you can always, as this stuff is recorded, you can always go back and see it again. So we're going to clean this up for the sake of clarity. This goes away. To deal with these problems though, what we have to do is, well, to figure this one out, to figure out the magnetic field on the inside of this solenoid, is we're going to simplify stuff a little. In reality, what we have is that okay, I think I'm good. The magnetic field looks like this. A magnetic field of a solenoid looks like this. So there is some magnetic field on the outside. There is a lot of field on the inside. But we will simplify our picture by saying the following. So let's say this is the solenoid. We will say that the magnetic field on the outside, beyond the outside, is very weak, which is true. It is very weak, and we will in fact just approximate it to be 0. And we're going to say that the field on the inside is not just strong, but that it is also constant. And it's along these straight lines, which is true to a good extent. If you look at the picture of the actual field, the field, roughly speaking, stays linear and constant throughout the inside of the solenoid. But once you get to the edge of it, you will see that it curves a little. So it's no longer true that it would be constant out here, but we will ignore that piece. We will say that the magnetic field here is roughly 0. So on the outside, it's roughly 0. That's not quite true, but this is what we'll do for the sake of the problem. And then on the inside, so the field on the inside, is we're going to say that this is roughly constant, which is true to a good approximation. All right, so given these things here, let's go ahead and try to solve the problem. And so we have the solenoid here with a bunch of loops. Maybe we'll add one more. Comes out, and then there's a wire here that comes out, that the current flows into this thing, and then eventually somewhere here on this side, the current flows out. Here's I. We will need a length of this thing somewhere at some point. We will need length. So let's assign length of this solenoid. This stage, the length of this whole thing is L. And I think with that, we're probably good to go on. So the Amperes law is B dot L equals mu naught times I enclosed. And the integral itself is over a loop that is closed. So we need to determine what loop would work for our purposes. And, well, I'm going to tell you what we'll do. Here's what we'll do. We're going to take a little segment. The loop we'll take this time is just going to look like this. This is going to be our loop. And note that what we get is that, well, what if we were to label this segment of the loop here? Let's label this segment of the loop first segment, this segment of the loop as the second segment, this part of the loop as the third segment, and so then we will label this part of the loop as the fourth segment, so that we have 4 segments. In other words, this integral here on the left hand side of b dot dl, where I integrate magnetic field along the path chosen all the way around the closed loop, that would just amount to b dot dl along the first part of the loop plus b dot dl along the second part of the loop plus same thing along the third part of the loop, and then the fourth part of the loop as well. So this way I complete the full loop. It has to be a complete closed loop. Now let's see if we can play around with this a little. So let's consider the first loop here. So if we look at the first loop, what we have here in this picture is that the magnetic field here, B, at first the magnetic field is perpendicular. Look at that here, between dl. So here's the element dl, and here's B. So this element dl is perpendicular to the magnetic field E. And then once you move outside of the solenoid, let's say you're here, and here is a new element dl. At this point here, the magnetic field is 0. So all of this then amounts to 0. Because cosine of the two vectors that are parallel, perpendicular, if you do the dot product between them, you end up with 0. And so for however long the magnetic field is present here along this path, the dot product would still be 0. B dot dl would be 0. And then after that, the magnetic field is 0, so it would just be still 0. Now the second part, along the second part here, all of these little elements dl multiplied by the magnetic field would amount to 0, because the magnetic field here is approximated to be 0. So from the second one, I get 0. From the third one, if you look at the third one, this is the same story as with the first one, the first segment of the loop. So if I take a segment of a loop here, call this dl, I would be multiplying this little dl times the magnetic field on the outside, which is 0, so that's going to give me 0. And then eventually when I enter the solenoid, what I would have here is a little segment dl that would be dotted with a magnetic field, but the two are perpendicular. I have 90 degrees here. Two are perpendicular, and because they're perpendicular, the dot product would be 0. And so this one is also 0 for the same reason as the first integral here was 0. The only thing left is this. Now, in the fourth segment, I have dl's, all of the dl's point in this direction, to the right, and so does the magnetic field. So in the fourth segment, what I have is that the magnetic field is parallel to the dl, all of the dl elements. And so this here then becomes b dl times the cosine of 0. This is over the fourth segment, and then b is constant. So I'm going to put here b is constant on the inside. And for that reason, my integral b dot dl simply becomes b dl over the fourth segment. And that would just imply, well, the fourth segment here that I want to take is arbitrarily long, and so why don't we just make this thing as long as the whole solenoid? So let's make this fourth element as long as the whole solenoid. This way we have some kind of a length that we can refer to. And so we'll turn this into B times L, where L is the length of the solenoid. Okay, so I figured out the left-hand side of the equation. So now what I can do is I can take this and I can rewrite this as magnetic field on the inside. So I'm going to put here inside, magnetic field on the inside of the solenoid times the length of the solenoid equals mu naught times I enclosed. Right, now we have to figure out this I enclosed. So what I'll do is I'm going to redraw this like this. Here's the loop that we took. I enclosed, that's the current that is enclosed by the loop. And so the length of this loop is L, the length of the solenoid. And then how much of the current goes through it? Well, the wire comes up and then it goes through. Here's current, and then it goes on and comes back again and again and again and again and again and again. That means that I have all of these currents that come at me every time a wire passes through the surface of this loop. And every single one of these is the current I. I have a solenoid here, comes through this loop. And so in that case, what I have to say is that I enclosed is equal to the regular I, the I in the solenoid, times N, where N is the number of loops that I have. So N is the number of loops in the solenoid. And so this equation then becomes B on the inside times the length of the solenoid equals mu naught times I in the solenoid times N. And now I have my expression for the magnetic field on the inside of the solenoid. It's just going to be mu naught times I over L times N, where N is number of loops in solenoid. Okay, this would be the magnetic field on the inside of the solenoid. Okay, and here's the last one. So the magnetic field of a toroid. Toroid. Find the magnetic field on the inside of the toroid. So the picture is here, but let's see if we can sort of make sense out of it. So suppose you take a solenoid. Here's a solenoid. Current flows into the solenoid, flows out of the solenoid. So the current flows in, and then eventually it flows out of the solenoid. And it generates a magnetic field. And the magnetic field is constant on the inside, or at least that's a very good approximation. So we have the magnetic field on the inside. That looks like this. Now if you take this solenoid and you bend it into a circle, you're going to end up with, so here's a solenoid, you bend the solenoid into a circle. That, and then you have all of these coils of wires go around. And a much better picture is here on a white background, but anyways, this is what we get. Then it should be pretty easy to see that the magnetic field would just follow this bent solenoid in this fashion. And all of the magnetic field of this toroid would be contained on the inside. I'm going to draw one more line of the magnetic field. Yeah, missed it. Oh well. So the magnetic field on the inside of the toroid would just look like that. Right, so now let's use the Amperes law to figure this out. So B dot dl was mu naught times I enclosed, and B dot dl is done over a closed loop. So let's pick a loop here along which we would like to integrate the magnetic field. It should be pretty obvious that the loop you would want to do would be this. Reason being is that if this is the loop you choose, then all of the elements dl along this loop, dl here, and put another dl here, You put another DL here. All of these little DLs would be parallel to B, the magnetic field. That's good because that means that the Amperes law is actually useful in this case. So what you would have then is that B that DLB is parallel to the DL. Well, comes the integral of B DL cosine, which is just, still have to make sure that we actually integrate this along the whole path. Well, it's mu naught times I enclosed. Now B is constant everywhere, and that comes from here. We know that B on the inside is constant. B on the inside of the solenoid is constant. So if you take the solenoid and you bend it into a circle, then B here would also be constant. It's a good assumption that this is the case. And so now we will, if B is constant, then I can pull B out of the integral. And so I'm going to get B times DL, where I want to make sure that I integrate the entire length of the loop, equals mu naught times I enclosed. All right, the integral over dl is just going to give me the length of the loop. So let's, here's the center of the toroid, and then here's little r, where this little r is the distance from the center to my loop. And so this becomes b times 2 pi little r equals mu naught times I enclosed. Now little r would be the distance between B and A. And here's what I mean by B and A. So A would be the inside radius of the toroid, and then B would be the outside radius, or the radius to the outside of the toroid. So this is B. Right, so this goes to this point, this goes to this point, and then R goes to here. Right, now what remains to do is to figure out I enclosed, because what I have is that B on the inside of the toroid equals mu naught over 2 pi times I enclosed over R. I have to figure out the current enclosed. So let me draw it maybe here. If I have this loop that looks like this, and then I have all of these little elements DL all over the place here. They move around. Maybe I'll put 2 more on this side, so you have these elements DL. And the magnetic, or rather the current, will do the following. See, the current follows the wire, and the wire does this. It comes over this loop and goes into the loop. Over this loop, goes into this loop, comes over this loop, goes into this loop, all the way around. That's actually not bad. And so this is what the wire does, comes over the loop and goes into the loop, and therefore the current does exactly the same thing because it follows the wire. And so everywhere in here I would have the current that goes into the loop. So then the enclosed, the current that is enclosed by my loop would just be, I'm going to put this here, I enclosed would be I times the number of loops, or the number of wires, number of loops that I have in the toroid. And therefore the magnetic field on the inside of the toroid would be mu naught over 2 pi times I over R times N, where N is the number of loops. And that does it. This is the magnetic field of a toroid. And I think this is it for the applications of the Amperes law. If you know how to do these 4 derivations that I showed you, derivations of the magnetic field using Amperes law, so toroid, solenoid, straight wire, and I thought we did another one. Anyways, if you know how to do these 4, then you should be good for the Amperes law.